All right, so in this video, we're going to talk about briefly the idea of a centroid. And so before we get to what an actual centroid is, we need to build up a few ideas before that. And so you'll see here I've got some definitions laid out on the screen. We'll start with moment. A moment is defined as the tendency for mass to produce rotation at a point. Then we'll go down to a lamina, which is just another name for a thin plate of constant density. This whole idea of constant density, many times you'll refer to this as, or you'll hear referred to this as homogeneous. So anything of constant density would be defined as homogeneous. The density formula that you may have seen again before, maybe a physics class or a chemistry class, would be defined as mass over area. That's the Greek letter delta, mass over area. A center of mass, which I know everybody's familiar with, happens to be a unique point, meaning there's only one. We use the notation x bar, y bar, where a single particle of mass would have the same moment as the original whole system. So would have the same tendency for mass to produce rotation at a point as the original whole system. And then a centroid is just a very specific center of mass. It's a center of mass for a homogeneous lamina, one with constant density. And those are the types of problems that we'll take a look at in this section. Now, okay, so in the first example, we're given these two curves now, and we're going to try to find the centroid. So for the centroid, I'm going to start off with an actual graph here of what it is we're going to be looking into. So here's going to be our cube function, and here's going to be our square root function here. Now, clearly the region we're interested in is this guy. And so to get this set up, the first thing that I always recommend doing is finding A, right? A is going to be a part of all the x bar and the y bar, so let's find it to start. So our A would be the integral, and the area of this thing, as we saw in earlier sections, would be the top minus the bottom. So the top would be the root x minus the bottom of x cubed dx. And if you set these two things equal to one another, you would find out they intersect here at 1. And so that's going to go from 0 to 1. When you compute that, you get 5 over 12. So now, for the x bar. The x bar is 1 over a. So 1 over 5 over 12 would just be 12 over 5. So I'm going to put that out in front. I'm still integrating on the same interval, 0 to 1. And then I have the x f of x. Well, the x is going to be easy. Just put that in there. But that f of x, like I pointed out, is still going to need to be that top minus the bottom. So we're still now going to have in here this root x minus x cubed dx. So because we have these two curves here, we're going to have a top minus a bottom for our actual height. And so when you compute that, this gives you a 12 over 15. The y bar is going to be somewhat similar, where we start off with this 12 over 5, integrate from 0 to 1. Now we have a 1/2. And for this case now, it's going to be that top squared minus the bottom squared. So top squared minus the bottom squared, followed by our dx. That ends up being 3/7. So our ordered pair, x bar, y bar, would be 12/15, 3/7. This is where the center of mass would be for this particular homogeneous lamina, hence the centroid of this particular problem. All right, so in this particular problem, this is an interesting one in the sense where we can really save ourselves a lot of work if we understand what this centroid actually is and what we're doing. Now, in the last problem, we had a square root and a cube, which are not symmetric, okay? If I gave you a square root and a squared, we could talk about a little bit of symmetry there possibly, but with a cube and a square root, not so much. In this particular problem, I've given you a quarter of the unit circle. Now, to get this thing started, we know that we would need to figure out A. A is going to be the area. So in theory, we have the integral from 0 to 1, since that's a 1, of root 1 minus x squared dx. Well, you really aren't in a position to compute this just yet because that's technically a Calc 2 integral. So instead, it's just a quarter of a circle. So we would do 1/4 pi r squared, which would just give us the pi over 4. So a little bit of geometry there goes a long way and saves us a big messy integral. The other thing that we know is that symmetry is a very big part of this. So if you picture this as something with constant density and you're trying to balance it, you know that it's going to balance somewhere along the line y equals x, which means that our x bar must equal our y bar. So if we compute just one of those, then the other one's going to be the same. So pick your favorite, it doesn't matter. X bar would be our 1 over a, so 4 over pi, integral 0 to 1, x times the square root of 1 minus x squared dx. This integral is a whole lot easier. Now you just have a u sub, which takes care of this guy, and it falls apart pretty quickly. This ends up being a 4 over 3 pi. Since we made an observation at the beginning that x bar has to equal y bar, we know that y bar also has to equal 4 over 3 pi. Therefore, the centroid would be 4 over 3 pi, 4 over 3 pi as an ordered pair. So when it comes to these types of problems, because they're truly centroids and because we're talking about a constant density, a homogeneous lamina, by all means, feel free to use symmetry to speed up the process and help yourself out if possible. You just have to be certain that the area, the region of the area is going to be symmetric and allow yourself to do that stuff. Go ahead and I've put the formulas up here for the x bar and the y bar in order for us to figure out this centroid. So you'll see the x bar would be the x coordinate of the centroid, and it's got a formula as 1 over a, this guy. Y bar would be 1 over a, this. But I also want to point out a couple things. The a underneath is the area, and we saw that a little bit earlier, and we also know that the area is going to be computed by this right here. I also need to point out to you that this is, again, a very generic formula in the sense that if you're given one curve, that's great, but if you have multiple curves, you need to adjust. So just to be clear on this f of x right here realistically is going to be a top minus a bottom, and this f of x squared right here realistically might be a top squared minus a bottom squared. And we'll take a look at some examples and see how these formulas relate.